Hi guys, so in this video we'll be doing the third lesson of Unit 6, so 6.3, which is on measures of spread. So first off, what do we mean by measure of spread? Quantities that indicate how closely a set of data clusters around its center. So how spread out is the data? Is all the data close to the center? Is it really spread out far away from the center? So that's what we're going to talk about today in terms of measuring the spread of data. Okay, so a couple of definitions here before we get into the example. So deviation is the difference between an individual value in a set of data and the mean of the data. Okay, so basically you take each of your values, right, individual values, and see how far away they are from the mean. So example, if our course mean was 80 and your mark was 83, you would do 83 as your x value minus 80 as the mean. That tells me the deviation for your mark is 3. Okay. If your mark was 70 and the average was 80, you would do 70 minus 80. The deviation or the calculation will give us negative 10. That will tell me that you are 10 away from the mean. And the negative tells me that you're going to be 10 below the mean. Okay, so there's deviation. Another term we will talk about or use is variance, and the variance is the average of the squares of the deviations from the mean. Okay, that sounds complicated, but once we do the example, it should make more sense. And when, as always, with a little bit of practice with this stuff, it should become hopefully fairly, if not easy, but you should be able to understand it a lot better. Okay, so we have population variance where you can see mu, right, which we talked about in one of the previous lessons. And then we have sample variance. So if we're dealing with a sample, our mean is represented by x bar. Okay. The other differences in the two formulas here, you'll see in population variance, we use sigma over here, whereas in sample, we use an S. Okay, so population variance is represented by sigma squared. Sample variance is represented by S squared. The final difference would be the denominators. So in population variance, the denominator is just n. In sample variance, the denominator is n minus 1. And the reason we subtract that 1 is because it compensates for the fact that a sample tends to underestimate the deviation. Because samples will underestimate the deviation, we do this subtraction of 1 to try to compensate for that. Okay. How you calculate it, we'll go into more detail in the example, but basically x represents each of your individual data points, and then the mu or the x bar represents your mean. So you take each data point, subtract mu, and square it. So your first point, subtract mu, square it. Your second point, subtract mu, square it. Your third point, subtract mu, square it, so on and so forth until you've done that for all of them. You add those all up and divide it by the number of data points that you have. That will give you your population variance. And it's the same formula for sample variance, except for instead of dividing by the number of data points that you have, or the number of values that you have, you take the number of data points or values that you have and subtract 1 for your denominator. Okay, so those are the definitions that we will be using or needing going forward. In terms of, one more definition here, is standard deviation. So we talked about deviation being how far each individual data point is from the mean. How do we calculate standard deviation? Well, basically the standard deviation, if you notice here, looks very similar to the variance. Okay, so standard deviation is the same formula as the variance under the square root sign. And then basically you square root it. So standard deviation is sigma squared, whereas standard deviation, the variance is sigma squared, whereas the standard deviation is just sigma, which equates to the square root of the variance. Okay, hopefully that made sense. Let me say that one more time. Going back, standard deviation, if I scroll down here, is sigma squared. There's the formula. Or S squared if it's the sample variance. To figure out your standard deviation, you're basically taking the square root of the variance. Okay, so if it's a population standard deviation, represented by sigma. If it's a sample standard deviation, it's represented by S. Okay. looking at our example here. So a building maintenance company tracked the number of months that fluorescent tubes lasted in all offices in a building. Okay, so we're going to change this just so we're clear. We're going to call it all offices in a building because by saying that, it makes a difference in how we're going to calculate and which notation we're going to use. Okay, so we're asked to calculate the mean, variance, and standard deviation. So because our data is data for all of the offices, that means we're dealing with the population. Okay, because we're dealing with the population, for mean, we're going to use mu. For variance, we're going to use sigma squared, and you'll notice down here where my cursor is, we're going to use the formula that has the n in the denominator, not n minus 1. Okay, so just be careful that you're using the correct notation and formulas based on whether you have a population or whether you have a sample. Okay, so in this case we have a population, so we'll be using all the formulas and notation corresponding to population. Okay, so here are our points, or all of our data right here, listed from 8 up to, well, 8, 29, 22, 15, 10, 22, 12, 4, and 22 again. The best thing you want to do here is create a chart with all of your data. To make it easiest, I would do it in order, numerical order. I guess you don't really have to, but just so you make sure you're not missing any of the numbers. You can see all of our individual data points are here in the first column. Second column is our mean, or our average. Third column is going to be each data point subtract the mean, and the last column is each data point subtract the mean squared. Okay, and the reason we're going to do that, or hopefully you've already figured it out, that the reason we're going to square it here is because we need that value to figure out our variance. Okay, but before we get there, let's go in order here. So the first thing we're asked for is the mean. So the mean, hopefully, is fairly straightforward. Add all of your data points together and subtract by the number of data points that you have. So add them all together. There's 9 of them. Divide by 9 tells us our mean is 16. So in the column where we see the mean, we're going to write 16 going all the way down. The next thing we are asked to figure out are the variance and the standard deviation. If we can figure out the variance, right, we know the standard deviation is the square root of the variance. So let's figure out the variance first using our population variance formula. So note that we have sigma squared, we have mu, and then we have the capital N here and the denominator. So what we need to figure out is the sum of x minus mu squared. So what we did in the third column is x minus mu. So basically 4 minus 16, negative 12. 8 minus 16, negative 8. 10 minus 16, negative 6. So we did that for all of our data points. And that gave us x minus mu for each data point. What we need, however, is x minus mu squared. Okay, so now we're going to take each of the numbers in this column for x minus mu and square them to get these values here. Right, so here, negative 12 squared, 144. Negative 8 squared, 64. Negative 6 squared, 36. So on and so forth, all the way to the bottom. Okay, so that gives us x minus mu squared for each individual data point. And what we need here, remember this symbol right there is telling us we need the sum of x minus mu squared. So adding together all of the numbers in the x minus mu squared column gives us 538. So this numerator is 538. The n value is 9 because we have 9 points, or 9 numbers in our data set. Okay, so the last thing we need to do then is take our x minus mu squared, the sum of all of our x minus mu squared, which is 538, divide it by 9, and it tells me my variance, sigma squared, is 59.7. The last part of the question asks us for standard deviation, and we know the standard deviation is the square root of the variance. Okay, here you can see we used 538 divided by 9. Just to give us a more exact number, because this is rounded here to 59.7. So to get a more exact number of the square root, we can use this 538 over 9, square root that, and that tells us the standard deviation is 7.73. Okay, so now we've answered all 3 parts, the mean, the variance, and the standard deviation as asked in the question. Okay, moving on to the last bit here. Another term that we'll get familiar with is z-scores. And what does a z-score tell us? It is the number of standard deviations the datum is away from the mean. So basically, you could take any specific data point and calculate the z-score for that data point, and whatever the z-score is, that number tells us how many standard deviations that data point is away from the mean. Okay, so again, let's try doing an example here. Actually, before we get to the example, again, we need to distinguish between population and sample. And you can see here, the formula is x minus the mean, so mu for population, x bar for sample, over the standard deviation. And again, sigma represents the standard deviation for a population, and S represents the standard deviation for a sample. Okay, so regarding the previous example, right, so the example we just did with the offices and the tubes, what would be the z-score of a tube that lasted 17 months? So let's say one of our data points was 17 months. Figure out the z-score, and because it is a population, we're going to use the mu and sigma notation. So 17 months is our x value. The mu we know from the question above, or in the last slide, is 16. And we also solve for the standard deviation, the sigma, which is 7.73. So x minus mu over sigma, x is 17, mu is 16, and the standard deviation is 7.73. Calculating that tells us that a tube that lasted 17 months has a z-score of 0.13. Okay. Again, what does the z-score tell us? It tells us how many standard deviations our datum, or this piece of data, is away from the mean. So if a tube lasts 17 months, that means at 17 months, we are 0.13 standard deviations away from the mean. So that should make sense. 17 is really close to the mean, which is 16. So we should be getting a very low number, a number below 1 for sure, because we're so close to the mean. So let's say if the z-score had been 1, that means we're 1 standard deviation from the mean. That means we would have been 7.73, which is the standard deviation, 7.73 away from the mean. So if we did 16 plus 7.73, which is 23.73, 23.73 would then be 1 standard deviation away from the mean. Okay. So anyways, without getting too complicated here, to answer our question, the z-score for a tube that lasted 17 months is 0.13, and that means 17 months means that piece of data is 0.13 away from the mean. Okay, and that's what the z-score tells us. What you can do, and obviously with any lesson that we've done on video, or pretty much any lesson obviously we've done even in class in person, the textbook has examples. So if you want to read through all of the examples to get a better understanding of this stuff, you can. But page 280, example 1, goes over variance and standard deviation and what they mean. So it's a good example to read over. But by all means, read over the other examples as well before going on to the homework if you need to. Okay, and that's it for today's lesson. Thanks, guys.